Hi everyone, I'm Alexandru Ianta, and today I'll be talking about Tangled program graphs, a genetic programming framework, and what marking schemes in TPG are, and how they affect performance when benchmarked against the Atari learning environment. So just as a quick recap, the arcade learning environment is a Python library for reinforcement learning research. It provides us a collection of Atari games with a common interface that we can easily connect our agents to. This enables us to do training and testing in these environments. Training or testing an agent consists of having an experiment script run the agent through playing a game in the arcade learning environment. First, the arcade learning environment computes a frame and produces a game state vector as well as the current score or reward at that frame. We first downsample this game state vector and then flatten it before passing it to TPG as an input. TPG then produces a numeric value, that it will be an integer, which is mapped to one of the valid actions that can be applied to the current game. We then apply this action to the game, which will produce the next frame, and then the loop repeats. Before getting too far into marking schemes, let's review some TPG concepts. At its core, TPG involves simple register language programs, which we run on the input vector. Learners encapsulate these programs and use them to produce bids. Teams organize learners into groups, and during a round of bidding, we select the learner with the highest bid to suggest its action, which is an integer that represents a valid action in the game environment. However, learners can also point to other teams, in which case the bidding process starts over. Let's make this more concrete by visualizing it. An instruction in TPG program has a mode, an operation, a destination, and a source. The destination and source fields correspond to indexes into either the register set or the input vector, from which we will retrieve values that we will apply an operation to depending on the value in the operation field. A collection of these instructions form a program, and after we run this program on an input vector, we will create some sort of value in R0 that acts as the bid for the learner that encapsulates the program. Learners are attached to teams and can point to either a discrete action which we can apply to the game state or other teams, in which case we would begin the bidding process again. Keep in mind that teams can have multiple learners. Traversals in TPG refer to the process through which we take an input vector and produce an action that we can apply to the game state. All traversals begin with a root team, that is, a team that has no other incoming edges. All the learners attached to the root team are run to produce a series of bids. The learner with the highest bid will be followed. If that learner is pointing to a team, we move to that team and repeat the bidding process again. If that learner is pointing to an action, we return that action to be applied to the game state. During mutation, variation operators can create highly complex graphs with these teams and learners. These graphs may contain cycles. During a traversal, however, it is imperative that we do not get stuck in one of these cycles. This is where traversal strategies come in. In previous work, we used something called a team traversal strategy. With this strategy, we ensure that we never revisit the same team twice. In this work, we explore an alternative traversal strategy wherein we never revisit the same learner twice. Because both of these traversal strategies involve marking either teams or learners as already visited, they can also be referred to as marking schemes. Let's consider how the team traversal strategy might play out on a Tangled program graph that looks like this. Note here how we couldn't return back to team 1 from team 3 because we had already visited team 1. Now let's take a look at the same graph under the learner traversal strategy. Note how there's no problem returning to Team 1 because we are not revisiting any edge that we've already seen. Let's look at both of these traversals one more time to highlight the difference between them when trying to resolve the action to be applied to the game state. To assess the difference between traversal strategies on TPG's performance, we chose 18 Atari games from the ALE to train populations on. For each of our two strategies, we ran 5 experiment instances, for a total of 180 experiments. After training, the champion root team from every population was evaluated over 20 episodes of play. During this evaluation, we kept track of fitness, but also of static and dynamic properties which we felt could help us characterize the differences between these traversals. These include things such as the average traversal depth and the average number of instructions executed to produce an action. There are also many more to be read about in the paper. An agent's fitness is the score it achieves in the Atari title that it is playing. Different Atari titles have wildly different value ranges for the scores that they will give out. This made it difficult to compare fitness between our experiments. To provide a uniform metric for comparing fitness between Atari games, we normalized TPG's score against the one achieved by Rainbow, a leading model-free deep learning approach to the arcade learning environment. On the fitness curves shown here, 100% on the y-axis indicates that TPG matched Rainbow's performance for that title. Values over 100% indicate TPG outperformed Rainbow. Values under 100% indicate Rainbow outperformed TPG. Here we have the average normalized fitness achieved by TPG champions during testing after their training is completed. For each environment, we have the results for learner traversals in blue and team traversals in orange. You'll note that for most titles, performance is very similar between the strategies. Notable exceptions include Fishing Derby, where learner traversals performed better, Frostbite, where team traversals performed better, and Venture, where learner traversals performed better. Note the log scale on the y-axis. Here are the test results again, this time normalized against Simple, a model-based deep learning algorithm. Again, it is important to note the log scale on the y-axis. For Private Eye, Asteroids, Fishing Derby, Bowling, Cruel, and Battlezone, both traversal strategies outperform Simple by a wide margin. For the Freeway title, both strategies perform only a little better than Simple. Under Frostbite, team traversals managed to outperform Simple, whereas learner traversals only managed 2/3 of Simple's fitness. For the remaining titles, Simple outperforms TPG. There doesn't appear to be a clear, better traversal strategy in terms of achieved fitness. Larger differences between the traversals were observed in terms of the number of times that they made use of particular actions in Atari games. We can see that learner traversals used the up action more than twice as much as team traversals, whereas team traversals used up fire and down right far more often than their learner traversal counterparts. This suggests that while the achieved fitness is comparable, the different traversal strategies discovered different techniques to achieve it. Some of these strategies can be seen here, with the bowling agent slowly discovering how to hit the middle pin, and the classic asteroid strategy of spinning in circles and firing so as to not having to deal with the inertia of the spaceship itself. While there was little difference in terms of raw fitness between the traversal strategies, The subtle differences in the kinds of techniques they develop to achieve those fitnesses are nevertheless interesting and merit further research. Expanding the experiment to more Atari titles can help uncover any larger trends, while it may also be interesting to design hybrid agents that make use of both learner and team traversal strategies. Nevertheless, I hope this presentation provided some insight into what TPG is, what traversal strategies are, and how they impact TPG agents. Thank you for your time, and feel free to reach out to me with any questions or comments.